How much heating energy can you save with a thermal insulation? Which measures are worthwhile in your case? Hi, it's Klaus again from electronics.unmessed. Today I'm picking up an idea from Mika, who is one of my followers. I think he is not the only one wondering how to improve the thermal insulation of his family home. That's why we both put a lot of effort into making a tool that will help you educate yourself to make the right decisions. Everybody knows that there are ways to reduce energy consumption through thermal insulation and through your own behavior. With our little tool, you can compute yourself which measures could be worthwhile for you. We could say that today's episode is about thermal energy.unmessed. Of course, we use an Excel tool for this, which you can download. Let's first understand how the computations work in principle. They are not as trivial as I thought in the first moment. We first look at the temperatures in the environment and in the house. The thermal energy emitted by the heaters is distributed throughout the house and is lost to the outside and into the ground via the outer walls, roofs, windows and doors. Incidentally, it is similar with cooling by an air conditioner. The thermal energy then just flows in the opposite direction. From the temperature differences at the boundary areas, we can calculate the heat energy flows and in turn the energy consumption. The thermal energy also flows between floors through the ceilings. This part of the thermal energy remains inside the house. We take all these heat flows into account in our calculations by considering the temperature differences, the thermal conductivity coefficients, and the size of the interfacing areas between the spaces. As already mentioned, this works not only for heating but also for air conditioning. Now you might have the idea of playing with the temperatures or checking what advantages thermal insulation could bring to your residential house. To do this, you simulate your house on the current status and in comparison with improved thermal insulation, better windows, etc., that can reduce the energy demand. And in the end, we calculate the heating costs or the air conditioning costs to see the savings effect of our individual measures. Of course, you can then make a cost effectiveness calculation based on the energy costs saved. That's the idea. If you want to calculate the thermal energy consumption using a real example, then a piece of paper and a pocket calculator are not enough to carry out these calculations. We will see why in a moment. On the one hand, many different heat flows at our interfaces have to be taken into account, outwards through the roof, through walls, through windows and through doors. In the basement, there is even a flow of heat energy to the ground. On the other hand, the individual heat flows depend on the temperature difference, the size of the interface, and the so-called specific thermal conductivity coefficient U, which depends on the material used. This calculation alone would be quite time-consuming to carry out on a piece of paper, especially in case you want to vary some inputs. But now comes the real difficulty, which is practically impossible to do without the support of a computer tool. In practice, it is usually the case that the attic and the basement, for example, are not heated. In order to calculate the heat fluxes that go through these rooms, We have to calculate the temperatures that we will get in these rooms after some time if we turn off the heating there. From our experience we know that without heating it is not quite as cold there as outside, because heat energy flows through the ceilings. However, calculating the actual temperature that will remain in a steady state is not an easy task. I used the so-called mesh flow method for this. If you are interested in the details, the rules were formulated by Gustav Robert Kirchhoff in 1845, after they had already been discovered by Carl Friedrich Gauss in 1833. I will explain briefly how it works in principle. The network you see here is an equivalent circuit for the thermal energy flows. The circles are sources that have known temperatures. On the left we have the outside temperature TO and the Earth temperature TE. On the right we have the temperatures on our 4 floors, TA, TF, TG and TB. The thermal conductivity values between the different rooms, the outside air and the ground, result from the individual thermal conductivity coefficients UA and the size of the boundary surfaces A. The values Uij describe the thermal coupling of the individual rooms we are talking about. For our calculation method, however, we need the thermal resistances instead of the thermal conductivity values. Therefore, we take the reciprocal values to get the thermal resistances RAI, RFA, etc. With the switches in the equivalent circuit diagram, we can turn the heaters on or off on the different floors. This will either enforce the temperature we set on the thermostat, or, if the heating is off, we get the temperature resulting from the heat flows from the adjacent rooms. For the switches, we use the resistance 0 for closed switches, and for open switches we use the value 1000 for the simulation calculation. An open switch actually has an infinite large thermal resistance. However, we cannot use infinitely large values for numerical computations. Our trick is that we use a very large value instead. Mathematically, we can represent the relationship between the heat flows Pi and the temperature differences delta T using a matrix U of thermal resistances Rij. The matrix U multiplied by the vector of all heat flows Pi gives the vector of the temperature differences delta T. The inverse matrix of U multiplied by the vector of all temperature differences delta T gives the vector of the heat flows Pi. Don't worry, it just looks easy, but it's about to get complicated now. Now here is the matrix U dependent from Rij, describing the network of thermal couplings. I had to think about the problem for a while to find this solution. Finally, I remembered a method that I had to learn very early as an electrical engineering student. As said, it is the mesh current method. It is derived from Kirchhoff's laws and is often used for electrical networks. I used it by analogy for thermal energy flows instead of electrical current flows. All mesh currents are drawn in the equivalent circuit diagram, and then the elements of the matrix U dependent from R, I, J are dependent via the couplings of the thermal energy flows in our case. Each row of this matrix corresponds to a mesh in the network. This gives us a matrix that contains all the thermal resistances of our model house. I also represented the switches as thermal resistors RSA, RSF, RSG and RSB. If we make these thermal resistances 0, then the heater is on. If we make them very large, the heater is off. By the way, the matrix must be symmetrical. Keep that in mind to cross-check whether you have applied the formalism correctly. Okay, so far the complexity looks relatively moderate. But for our calculations we need the inverse matrix. And folks, if we didn't have computers, fun would be over here. If I had to work this out for you by hand, we wouldn't be able to finish it today nor this week. Fortunately, you can do the matrix inversion with Excel, which of course we do. Okay, that was a little strenuous theory. Now let's see what came out of our tool development. And as always, when we do something like this, we put effort into developing the tool. It can do more than I originally thought. We have to make a few entries about the temperatures and the heating or air conditioning. On the left we see a very prominent analog display for energy efficiency. It always gives us immediate feedback on the thermal energy consumption in kilowatt hours per square meter and year. We call this the thermal energy efficiency value. This means that we can always see immediately whether a measure such as thermal insulation or temperature settings has a positive or a negative effect. At the top of the page we get the efficiency value broken down separately by heating and air conditioning. We enter the monthly mean outside temperatures during the day and at night for your region. A good source for this is, for example, the local weather service. We also need the temperature of the ground, which can be determined simply by measuring the temperature of the water in the home. Then we can decide whether we want to take into account the electrical energy that we use in the household for lighting, cooking, computers, etc. in our profitability calculation. In addition, we also decide here whether we want to take into account the thermal influence of the sun and the people living in the household. The sun can bring a lot of heat through large windows, and people also emit heat energy. This saves heat energy, and of course it increases the required cooling capacity of an air conditioning system. Then we can decide for each floor individually whether there is heating there or not. If we want to heat and cool, we set the switch to on. Then you have to specify the desired temperature for each month. If the switch is set to off, the temperature resulting from the heat flows to the adjacent rooms and the outside world are displayed in the second line. In the building prop and tariffs sheet, we need to specify the area size of our boundary surfaces, i.e. walls, windows, doors and false ceilings. In the second section, we give the thermal conductivity values of our interfaces. We get the information for this from the manufacturers of windows, doors, walls and thermal insulation material. For our profitability calculations, we can insert the information for the energy tariffs and the CO2 tax below. On the sheet Electricity, it is about specifying our power consumption so that we can estimate the waste heat from our electrical devices. At the bottom, we have totals for the whole year that we can compare to our actual electricity consumption. As said, it is only an option to consider this that we can choose on the previous sheet. On the sheet Settings, we can choose the division of hours between day and night. I choose 12 hours for each day and night here. However, you could choose any other breakdown that allows you to more accurately describe your own behavior. If we want to use the sun option, we also have to provide a few details. We estimate the strength of the solar radiation using the solar yield. I will link you to a video in the top right showing where to get the solar yield for any point on Earth. Then we need to define the windows where the sun radiation actually comes into your house. On the right side, we can indicate the presence of people and thus estimate the thermal energy that people give off. Then we get a printer-friendly report with an overview for the whole house. On the top left is an overview of the temperatures, and on the top right we get the efficiency classes of the individual floors. At the bottom right we get the consumption, CO2 values, performance indicators and of course the costs. If you now want to analyze more precisely where exactly how much thermal energy flows, then we can open grouped cells here. You will then receive a detailed list of the thermal energy flows for each floor. Positive energy flows outward, negative energy flows inwards. You can see for each month of the year how much energy flows out through the boundary areas or into the other floors. Cool, right? By the way, we are always happy if you subscribe to the channel. For those who are a bit more sophisticated, the matrix report provides all data of the heat energy flowing back and forth. You can even find out how much thermal energy is flowing from or into your earth ground. The two remaining sheets are machine rooms. Everything we talked about is calculated here. The heat energy flows, the temperature differences, heat outputs and the heat energy consumption. Of course, you could make that shorter, but I tried to keep this transparent. On one hand, this helps your understanding. On the other hand, it makes debugging easier for me. As said, the computations are not entirely trivial. The summary. We have seen how energy flows and consumption can be calculated from temperature profiles. This is very helpful to find out which structural measures can bring which energy savings and whether they are economical. We will soon see interesting examples of this on this channel. Maybe you want to do this analysis for your house too. Now stay tuned and don't forget to subscribe and support the channel. See you soon in the coming episodes.